Okay. Hello to everybody. As Gorast introduced me, my talk will be about multiplicity dependence as a proof of multiparton production mechanisms. My talk is based on materials which have been recently published in these four journal publications and has also partially have been submitted recently to archive. But in this talk, I will try to focus on the main ideas and avoid, whenever possible, all the technicalities. I would like to start discussion with inclusive production of different hadrons. We know that at high energies, everything is dominated by gluons. And a typical diagram for production of M, which is hadronic state, is shown here. M might include one or more hadrons. For the sake of definiteness, I will consider that I have just one meson final state. We understand that amplitude in this case is given by part of this diagram, and cross-section is actually square of this diagram. We understand that at high energies, gluons vigorously emit other gluons. And for this reason, actually, we should consider each gluon as a gluon shower, as shown here. And we know that after regionization, this gives us the Pomeron picture. To summarize, cross-section is dominated by Pomeron fusion. This is Pomeron 1, Pomeron 2. We know that diagrams which include more than one pomerons are usually disregarded. And indeed, it is justified when gluon densities are quite small. For example, when X is not very small. When, for example, we have sufficiently large hadronic scale wave, such as alpha S is small, or in some processes, we might get even stronger suppression due to high twist effects. In that case, instead of 1 over logarithm mu, we have 1 over mu squared. It's much stronger. However, this nice picture does not work at very high energies in BFK regime. We know that in this case, gluon densities grow vigorously, and this growth might compensate all the above mentioned suppression factors. So we come up to what is called the saturation regime. When it starts is actually quite open question. The situation is somewhat ambiguous now. On the one hand, we have models or approaches like KT factorization, which just consider gluon-gluon fusion and reasonably describe all the data. On the other hand, we have models which do take into account the saturation picture and describe everything in dipole approach, which takes into account all this. Fortunately, recent studies of multiplicity dependence could help us to solve this ambiguity and say how important or not are such corrections. And according to our estimates, the data clearly indicate that in LHT kinematics, 3 Pomeron contributions are pronounced. For the sake of simplicity, I will consider heavy quarks. In this case, it's theoretically the cleanest channel because we understand that Haas scale, which appears, is controlled by the quark mass at least, or might be even higher. And for this reason, perturbative approach is justified. I will start with the lightest of the hadrons, lightest of the quarkonia states. It's 1s quarkonium. The model for production of this quarkonia in PP collisions has been offered more than 40 years ago, and the so-called Carl singlet model. It assumes that we actually have a fusion of two gluon showers, like shown here, and due to quantum numbers of GPSI, we need to emit one more gluon here. This model gives a very decent description of data at very small PT, as well as PT integrated observables. However, we can see that at very large PT, above 10 GeV, predictions of models systematically underestimate the experimental data. The discrepancy is more than 2 orders of magnitude. For this reason, almost immediately when the model was when it was discovered that the model has problem, it was suggested that we should supplement it with additional channels, like for example, production of additional quark-antiquark pairs, additional mesons, etc. And this activity is going on up to now. Other approaches consider that instead of gluon-gluon fusion, we might have also other mechanisms like quark fragmentation or gluon fragmentation. More systematic way of doing things today is to consider is NRQCT, non-relativistic quantum chromodynamics. In this approach, we consider that we form two quarks, and these quarks might be in whatever state, color octet, color singlet, and with whatever spin parity states. And after that, with some probability, which is controlled by long distance matrix element, this quark-antiquark pair might fluctuate and form quarkonium. This is a very systematic and theoretical, very nice approach. But unfortunately, attempts to extract this non-perturbative long-distance matrix elements from experimental data have serious troubles. In this table, I show the values of color-acted contributions extracted by different groups. We can see that color-acted contributions shown here by red color vary almost by an order of magnitude. It's believed that this LDMs should be fundamental matrix elements, and for this reason, it's no way to explain why such discrepancy exists. Curiously, for other Quarkonia states, like for example Chi-C, Chi-B production, we do not have this problem. Here, the color singlet model or gluon-gluon fusion approach, in simple words, which is labeled here by P13 and shown by dashed colored curve, gives very decent description of data. Color-acted contributions are tiny and even frequently might be disregarded. Situation is very similar for Psi2S, Chi-B, and Upsilon-1S. So we need to understand what are the production mechanisms of GPSI and why we have this problem. As I will show a bit later, actually the problem is in these 3 gluon contributions, which according to our estimates might be quite sizable in case of GPSI production. But before that, we need to introduce one new observable. Actually, I mentioned earlier that if we have only inclusive cross-section, we cannot distinguish different approaches. For this reason, we will consider inclusive cross-section in which we will change the number of charged particles co-produced together with GPSI. Of course, we understand that we can consider full number of particles, but full number of particles is more difficult to measure. We understand that beams which are used to collect charged particles and beams used to collect GPSI actually might overlap or might not overlap. And experiment both situations have been studied. And curiously, results for multiplicity observable do depend drastically on this. Now I'm going to explain how this observable is related to the number of pomerons which participate in formation of Quarkonia state. We know local pattern hardened duality hypothesis, which has been confirmed in a number of experiments. That number of charged particles in experiment is proportional to number of patterns, that's to say, elementary gluons, which have been produced. According to BFK, we know the probability distribution to find n patterns when we have just one individual pomeron. Combining these two hypotheses, these two ideas, we can say that we should be able to tell if the pomeron picture is correct and if it can describe expected multiplicity dependence. But before comparing with data, I need to mention that experimentally variable p is strongly suppressed as a function of n number of processed particles, and this dependence is given by expression shown here, exponential minus lambda n. And n, the small variable, is actually number of particles divided by average number of particles. And this variable depends on average number, depends on energy, of course. For this reason, frequently we will discuss everything in terms of this small variable n. Next step. Now, when we discuss cross-section, usually it's more common instead of cross-section, consider self-normalized yield. What is it? We divide cross-section with n particles divided by cross-section with n equal 1. That's to say, without imposing any conditions on number of processed particles. And after that, we divide the same ratio by similar ratio in which we do not impose conditions that final state should contain quarkonium M. What is the physical meaning of this variable? If the sigma is probability to produce a given final state, that to say quarkonium M and n particles, or if we do not impose any conditions that any number of particles, then the self-normalized ratio has the meaning of conditional probability to produce quarkonium when we have uncharged particles in the final state. Obviously, this ratio doesn't include this strong exponential factor which is shown here. Experimentally, the self-normalized ratio has been studied, and it was observed that actually, as a function of n, it grows vigorously. Namely, it was expected originally that this dependence should be linear. We can see that situation is not so, and experimental data clearly rule out such linear behavior. It's difficult to explain this finding if we consider gluon-gluon fusion, no matter what waves of collected matrix elements we consider. And for this reason, this data clearly hints that possibly we could have sizable contributions of multi-Pomeroy mechanisms. I need to mention that originally this effect has been observed in AA collisions, and almost immediately it was considered as a clear signal of quark-gluon plasma formation. But later it was observed in PA collisions, and now it's seen in PP collisions. And clearly, in case of PP collisions, we definitely cannot speak about quark-gluon plasma in sufficient amounts. So obviously, this multi-pattern explanation is the only way to go. Quark-gluon plasma explanation is not applicable here. Now I'm going to stop briefly on multi-Pomeroy mechanisms and some technicalities related to evaluations. For our evaluations, we use color dipole model, also known as color glass condensate or CGC-SAT model. In the literature, when we consider this model, it's frequently assumed that the dipole cross-section is a universal object which already takes into account all possible interactions with the target. But before we continue discussion, we need to revisit what is included in the dipole cross-section and what is not. Also, we'll discuss how the heavy dipole cross-section depends on the number of charged particles produced per rapidity being eta during the scattering. We know that the dipole cross-section should satisfy the ballistic Chekhov evolution equation for rapidity. Effectively, in terms of Feynman diagram, this corresponds to resummation of fan-like diagram shown here. We know that there are a number of parameterizations, like for example CGC, BCGC, etc., which try to describe this ballistic Chekhov equation at least approximately, and thus effectively take into account all the diagrams. But these approaches do not take into account diagrams shown here with two or more Pomerons connected to quark lines. So we need to take them into account. When we consider just single Pomeron, then in high multiplicity events, we understand that we should nevertheless satisfy ballistic Chekhov equation, and the only thing which might change is the saturation scale QS. And the relation between QS and number of observed particles is actually linear. It has been studied in numerous papers, and here are details, and it works with precision of 40–10%. So this actually gives us receipt how we should introduce multiplicity dependence into dipole approach, which should just scale QS squared as a function of n. Now, I'd like to stop briefly. What is the relation of multiplicity of the whole process and multiplicity of individual Pomeron? Actually, we understand that there is a number of possibilities to connect Pomerons to hard amplitude. But if we consider, for example, all these possibilities which are disconnected from hard part, shown by blue lines, then after summation of all such contributions, we understand that they will cancel in self-normalized ratio. And for this reason, we should now focus only on the contributions, only on Pomerons which are connected to quark lines. We understand that results for multiplicity will depend on the way how the charged particles are collected. If the beams, this red square box used to collect charged particles, overlaps or not with the beam used to collect GPSI. If beams overlap, then enhanced multiplicity is shared by all Pomerons. And here we understand that we should sum over all possible partitions of the enhanced number of particles between these Pomerons. If beams are not, if bands do not overlap, separated, then enhanced multiplicity should be shared only between these two Pomerons which participate. Or if we are in this kinematics, then here, if we are collect particles here. If n is not very large, then the size of the dipole is controlled by the quark mass. So each hard Pomeron contributes a factor for the n to gamma, where ne is the multiplicity of a given Pomeron, and gamma is of order 0.7. And this implies that we should see clear difference between the situation how we collect multiplicity, as well as between situation if we have just two Pomerons or three Pomerons as a whole diagram. If we have very large values of n, then the size of the dipole is controlled by saturation scale, and situation becomes less clear. We understand that we understand that in the heavy quark mass limit, contributions of diagrams with 4 or more pomerons are suppressed, and for this reason, we can simply disregard them. Now, I'd like to stop briefly on technical details of evaluation. In the dipole framework, we assume that we work always in the rest frame of one of the hadrons, proton, and assume that gluon emitted from the other hadron fluctuates into a color dipole in collected state, which later scatters in the field of the target and interacts with one or two pomerons. In color-synced model, the cross-section might be expressed as a linear combination of color-singlet dipole amplitudes as shown here. Here I have shown this formula just to explain what are the main ingredients in our formula. It includes meson wave functions, dipole cross-sections, or more correctly, some linear combinations of color-singlet dipole cross-sections, perturbative gluon light cone wave function, and gluon emission wave function. For 3-pomeron contribution, we do not have emission of gluons, so we do not have this object shown in teal color. But instead of linear combination, we have some bilinear combination of 2 pomerons. Now, I need to mention that when we evaluate 3-pomeron contributions, there are different possibilities. When
you have 2 minutes.
Oh, thanks. I'm finishing already. We have actually different possibilities. One is when we emit gluon, and the one we do not emit gluon. Here and here, leading code and next to leading code diagrams have different final states, so they add up additively. This one can interfere with this one, so we should be more careful. Fortunately, it's possible to show that diagrams which include odd number of pomerons are connected to the same patterns as shown here might be seen only when we have experiments with polarized protons and numerically are very small. So we can disregard these diagrams and so add up additively cross-sections of this, and this contributions. In this figure, I just illustrate dependence on rapidity y and pt of hadrons, and I just wanted to say that description is nearly perfect. But it's not our main subject. Our main goal is to describe multiplicity, which presents more challenges. In case of GPSI, it's possible to have measurements when beams are separated, as shown in this graph, and when beams used to collect GPSI and charged particles overlap, as shown in this graph. And we can see the dependence on multiplicity is quite different. Here is much more vigorous compared to here. We can see that our approach, shown by solid line, perfectly describes experimental data. We can see that actual predictions of our approach are quite close to naive approximation when we just consider n elevated to gamma, with gamma equals 0.7, 0.75. Also, we can see that our approach can clearly distinguish contribution of 2 and 3-pomeron mechanisms. For 2-pomeron, we can see that behavior should be something like this. For 3-pomeron, something like this line and this line, and clearly underestimates the data. And this is not the problem of dipole approach, but problem of all approaches which consider 2-pomeron fusion picture. But 3-pomeron picture clearly can describe the data. Similar measurements also can be done for psi 2s, upsilon, chi-c, and chi-b. In case of GPSI production, in case of other 1s quarkonia, we can see that the results are actually quite close to GPSI, and it's quite easy to understand why. Because actually, when we consider self-normalized ratio, the quarkonium wave function might be approximated as its value r equals 0 point, and this value cancels in self-normalized ratio. We have residual dependence on energy and size of the quarkonium in this parameter gamma effective. For this reason, we have minor differences in predicted multiplicity balance. And for the case of 1p quarkonia, like chi-c and chi-b, situation is completely different. We understand that due to quantum numbers, 3-pomeron mechanisms simply can't contribute. And dominant contribution is 2-pomeron. And for this reason, dependence on multiplicity is much milder compared to what we have seen earlier. If 4-GPSI grows rapidly, as shown here, and has been confirmed by experimental data, for 1p quarkonia, dependence is much milder. We actually can measure this for any of these chi-c0, chi-c1, chi-c2 states, and also for chi-b states. We hope that experimentals will be able to confirm this result, and this would help to qualify the role of 3-pomeron mechanism in quarkonia formation. And finally, I'd like to stop briefly on D and B mesons. Evaluation here is quite similar to what we did for Quarkonia, but we have to take into account both 2 and 3 polymer contributions. We actually found that 3 polymer mechanism constitutes approximately 40% for D mesons at small pt, but decreases rapidly at high pt. And for pt above 10, it almost doesn't contribute. For B mesons, this contribution doesn't exceed 10% even at small pt. And here we can see a comparison of experimental data for multiplicity dependence with model predictions. It includes with 2 and 3 polymer predictions. We also can see that our model, which includes both 2 and 3 polymer contributions, can describe observed multiplicity dependence. So now I come to my conclusions. We actually found that the 3 polymer terms give sizable contributions in the LHC kinematics, and this is especially important for charm and the small pt kinematics. We found that inclusion of 3 polymer contributions allows to explain multiplicity dependence in both in open heavy flavor production and in Quarkonia production without additional model assumptions. Finally, I would like to mention that there is a possibility to measure directly the contribution of 3 polymer fusion mechanism. It's simple diffractive production shown here. When we have a process in which one of the protons is separated by rapidity gap from everything else, and this everything else includes production of heavy Quarkonia or open heavy flavor mesons as shown here. Diagrams which correspond to the amplitude is shown here, and this is x, this is rapidity gap, and after squaring this diagram, we get 3 polymer picture shown here. Evaluations here are quite similar to inclusive case, and if you're interested, you may find details here. And we found here that multiplicity here is actually also quite mild, and this would be a very interesting result which experimentals could easily confirm. Thank you for your attention.
Thank you for your nice presentation. Is there any question?
I see that Marcelo has some question.
Yes, Marcelo, please.
Thank you so much, Marat. I enjoy your talk. I have actually 2 questions. When you handle the case of 3 or more pomerons, I mean, you handle this according to the Siddikov equation. I mean, the fan diagrams come together before you have the fusion, or what's the idea?
Thanks for the question. I understood it. Now I will reply. Actually, as I mentioned, equation of Siddikov takes into account all these fan diagrams, but Siddikov doesn't take into account diagrams shown here. When I have two or more gluons connected to the same quark line, and for this reason, we take into account them separately. These fan diagrams are taken into account as a parameterization of the dipole cross-section, for which we use the MBCGC. But this we take into account introduced by hand because Siddikov doesn't include it in evaluations.
Okay, thank you. And the second question, here in such scenarios, there is no possible Oderon interference in the process, or not?
Thanks for the question. It's also very interesting. Yes, indeed. Potentially, we have to take into account contributions of Oderons. But usually these contributions are small, and to see them, we need to construct special observables. In these papers, we considered only inclusive processes, so we did not take into account Oderon contributions.
Okay, thank you very much. Thank you.